Let us look at the world around us. You see normal people, the type of activities that they perform in their daily life. Now, let us look at those who have intellectual deficiencies. So, primarily today what we are going to talk about is the perceptual processes. This is one of the cognitive processes that we would be discussing at length today. What we have seen here is that we have either an internal stimuli or we have an external stimuli, which is supposed to evoke a response in us. Say you see something and accordingly you respond to it. You have to cross the road, you see things around you, you see what is coming while you would be trying to cross it, and then accordingly you judge when to cross. You also know get a feedback how much you have moved on the lane, and accordingly you proportionately decide what to do, when to do and how much to do. Similarly, when you have say any other thing to do, in each situation you have an stimuli. This stimuli could either be from the internal world or it could be from the external world, and then this will certainly initiate a response. Now, each of these stimuli, they stimulate one of the sense organs. We have several sense organs, and immediately now we will be going through all of them at length, how they work. Say the previous case where you were supposed to cross the road, actually you were looking at things. So, the stimuli that you were receiving from the external world, it stimulated your visual sense modality, the eyes, and the entire vision process told you how to go ahead. You also had your auditory feedback, your ears received the sound from the external world and accordingly you responded. So, actually when we have the internal and the external stimuli that comes to us, it will actually what it does is that it would stimulate one of the sense organ, and once again the sense organs when they are stimulated, they trigger another signal that moves to the brain. The brain will process those signals, and this is how we say that we have sensed it. Okay. Remember one thing, that we have not yet attached a proper meaning to it. Okay. That part we will come little later. So, we will repeat this entire process once we have completed our discussion on the sense modalities. So, as you have seen here, whether you are a normal human being, whether you have intellectual deficiency, all that we do in this world is that our sense modalities, they receive sensation from the external world. At times we have stimuli coming from our internal environment, and then they will further get processed. The brain will receive those signals, it will process it, it will thereafter it will assign a meaning to it. This is what we were referring to. So, you have your eyes, you have your nose, you have your ears, you have your synesthetic senses, okay. And all these will gradually pass on the signal to the brain, and the brain will process it. What is important here is that the physical energy of the stimuli gets converted into impulses that gets onward transmitted to the brain, and then this entire process, okay, wherein the physical energy is converted into an impulse, so that the brain can process it, is called transduction. Now, once the stimulus is received, it gets transduced into signals that the brain is capable of processing. Here you see the network in the brain, and once the signal gets processed in the brain, it is only then when we actually sense what we have seen in the external world. Human beings have 5 important senses: vision, hearing, taste, smell and touch. In addition to touch, the skin also contains senses for heat, cold, pain and pressure. We will now go into the details of each of these sense modalities. So, let us now begin with vision. The visible spectrum extends from about 380 to 780 nanometers, and vision begins with the electromagnetic radiation that gets emitted from the object. Light enters the eye through the pupil, the cornea, the lens and the interiors of the eyeballs, and finally reaches retina. So, from the external world, the source of light remains somewhere. From the source of light, the light actually, the beams, they fall on the object, and those electromagnetic radiation that this object actually emits, it reaches our eyes and then it goes up to retina. The convex lens of the eye makes an inverted image fall on the retina. Remember, the lens that we have in our eye is convex, and therefore, the object that is actually present in the real world gets represented in an inverted shape because of this convex lens on the retina, and the shape of the lens changes in order to bring light from near objects to a sharp focus on the retina, and this process is called accommodation. Say when you are looking at objects which are too far off or objects which are too near to you, actually what you do is that you accommodate your eye. At times if you look at my eyes, you sometimes manipulate it, and when you manipulate it, actually you either allow too much of light to enter into your eye, or you restrict the entry of light into it, and this process wherein you actually try to manage the shape of the lens, so that you bring light from the near objects, so that the final image that you have on the retina of the object, it is very sharp, it is visibly very clear. We do this exercise, and this process is called accommodation. Now, retina is the light sensitive layer at the back of the eyeball, which contains 2 types of photoreceptors, the rods and the cones. Human retina contains about 120 million rod cells and approximately 6 million cone cells, and therefore, it is obvious that numerically our retina is dominated by the rod cells. Cones are dense in the fovea region of the eye, and this region of course has no rod cells. The rods peak in density in a ring approximately 3 mm, that is 80 degree from the center of the fovea. To fall on the photoreceptors, light passes between the ganglion cells, that is the M and the P cells, and the bipolar neurons. The bipolar neurons send the sensory signal back to the ganglion cells, and then the axons of the ganglion cells together form the optic nerve, which carries the signal to the visual cortex. Optic nerve carries visual information from the retina to the brain. Blind spot is the point where the optic nerve exits the eyeball, and therefore, it has no photoreceptors. Visual acuity is maximum at fovea and is graded from the fovea out towards the edge of the retina. When you look at the transduction process in vision, the rod and the cone cells contain photosensitive pigments. Rhodopsin is the pigment present in rod cells. It exists in the cis rhodopsin configuration when it is not excited. Once you excite it, it gets converted into the trans rhodopsin configuration after the light falls on it. The rod photoreceptors and the rod connected nerve cells through the retina are responsible for pathways concerned with night vision. They increase sensitivity of our visual system in conditions with very little ambient light, and this is called scotopic condition. The rod bipolar connects input from between 15 to 13 rod speculars in the outer plexiform layer. The axons of the ganglion cells together form the optic nerve which carries the signal to the visual cortex. Let us now talk about the visual pathway. At optic chiasm, some of the optic nerves from each eye cross to the other side of the brain. So, it is something like a crisscross type of a thing. So, it will cross from here, and the long fibers or axons of the ganglion cells then reach the lateral geniculate body of the thalamus, from where it goes to the primary visual cortex. If you compare the characteristics of the rod and the cone cells in terms of number, rod cells we have approximately 120 million rod cells. If you look at the number of the cone cells, we have approximately 8 million of them. In terms of their sensitivity to light, we find that rod cells are more sensitive than cone cells, whereas the sensitivity of the cone cells is weaker. The light and the dark adaptation is very high in the case of rod cells, and therefore, they respond more to light and dark, whereas cone cells they can respond to light, dark as well as colors. When you look at the dark adaptation time, rod cells they take approximately 30 minutes to adapt to darkness, whereas cone cells they take 10 minutes approximately to adapt to it. And of course, in terms of light adaptation time, we find that approximately 1 minute is needed by both the cells. For optimum operation, the rod cells of course know darkness condition, vision during night hours. Okay. Rod cells are very good at it, whereas cone cells are much more effective during daytime and when we have bright light. Location wise, we have already discussed that rod cells are most dense just outside the fovea, whereas cone cells are distributed throughout the retina, and it is of course most dense in the fovea region. In terms of neural connection to bipolar neurons, rod cells have a pooled connection, whereas cone cells have one-to-one connection. Look at this image, you get the feel of the visual spectrum. You see the gamma rays, the X rays and the ultraviolet rays, and then you have the near infrared, short wave, you have the middle infrared, you have the thermal infrared, of course, you have the microwave and you have the radio waves. So, basically you see here that you have different types of waves that come in. And when you look at an object in your real life, actually you have a limitation. All of us are capable of attaining a limited amount of energy that actually our eyes can receive, and this is called the visible spectrum. So, when you look at this full animation, you actually realize that we have a limitation in terms of what our eyes can process, and let us now understand that once we know that this is what our eyes can process, how does the visual system work? To comprehend the visual mechanism clearly, let us look at this video. Here you see the electromagnetic radiations emitted by various objects. As you already know, the visual spectrum extends from about 380 to 780 nanometers. The colors represent the visible spectrum. This is a color disc and this boy is aiming at it. We are trying to understand the visual mechanism. So, what did he see? To comprehend this, let us look into his eyes. The light from the colored disc entered the eyes through pupil, cornea, lens and interiors of eyeball. It has now reached the retina. What you see now is a photomicrograph of the rod and the cone cells in the eye. You are now looking at the ganglion cells, that is the M and the P cells and the bipolar neurons. The light passes between the ganglion cells and the bipolar neurons. The bipolar neurons send the signal back to the ganglion cells. Thereafter, the optic nerve carries the signal to the visual cortex. You now see the primary and the secondary visual cortex, that is visual area 1 mentioned here as V1 and areas 2, 3, 4, 5, 6, 7 and 8. Here you see the optic disc, fovea and blood vessels. The visual sensation in this boy is completed now. He was aiming at the colored disc. So, what did his brain see? The extension of the colored disc that you see with dashes shows the visual field of the left and the right eyes respectively. The part of the colored disc that you see next to the eyeballs show the respective projections on the retina of the left and the right eyes. The bright yellow light represents the movement of signal across the brain. Some of the optic nerves from both the eyes cross to the other side of the brain at optic chiasm. The neural conduction in the optic nerve reaches the lateral geniculate nuclei. The spread of colors on the left and the right sides show the inputs to the left and the right lateral geniculate nuclei respectively. Finally, the input reaches the visual cortex. Once again, the colors that you see in the part of the cortex represent the input that has reached the primary visual cortex on the medial surfaces of the left and the right hemispheres of the brain. It is worth looking that the full colored disc that the boy was looking at has been processed differently by the two eyes and of course, the two hemispheres of the brain. What is remarkable is that the parts of this information finally combine and we perceive it as a colored disc. Let us now talk about the auditory mechanism. As we saw the importance of visual spectrum in the case of visual sensation, similarly we have limitations with respect to our audible range also. We cannot hear each and everything. The audible range lies between 20 to 2000 hertz. Okay, remember that 1 decibel is equals to 50 hertz. The external ear has the pinna that we see hanging out. This is what we call as the pinna and a canal. This canal ends at the eardrum. It is called the tympanic membrane. The middle ear has 3 bones, the malleus, incus and stapes, and the inner ear has a cochlea. The pinna of the external ear is supposed to collect the sound energy from the external world. The sound falling in the audible range travels through the ear canal and strikes the tympanic membrane. The tympanic membrane, that is our eardrum, transforms sound into mechanical energy. The oscillation of the eardrum moves the 3 bones, the malleus, incus and stapes, and these 3 bones together are also called ossicles. These 3 bones are coned in a series and hence the sound energy is mechanically transmitted. It also gets amplified in this process. The bones of the middle ear relay vibrations to the inner ear. The inner ear sense organs are contained in a bony structure called cochlea, and this cochlea has 3 different canals: the vestibular canal, the cochlear canal and the tympanic canal. Oscillation of the stapes in the middle ear presses the oval window and the vibration enters the cochlea. The vibrations travel through the cochlea, which is a fluid filled canal. The pressing of the oval window also seals off the end of the vestibular canal of the cochlea. Waves in the cochlea reach the organ of Corti, which lies in the basilar membrane. The organ of Corti has numerous receptors that are called the hair cells. The pressure of the waves stimulates the hair cells in the organ of the corti, and if they bend by as much as 100 trillionth of a meter, the signal is then sent through the auditory nerve to the brain. Stimulation of hair cells generates receptor potential, which is processed by the brain. It is important to note that nerve impulses arising from a given region of the organ of corti are sensed as a particular pitch, and this is called as place code. You are now looking at the different decibels to understand what our ears can actually receive. You have the whispers from 5 feet away, the leaves rustling, the average office interior, the sound that we usually hear when we have the patter of the rain, a window air conditioner when it runs, then the normal conversation, heavy traffic, the vacuum cleaner and the dishwasher, the sounds that they make, and then of course, we have the high decibel sounds that have the potential of damaging our ear, like the air raid sirens, the jet plane, stereos that are run on full volume, the trains, the heavy trucks, the power lawn movers. So, this actually helps us understand that we also have a limitation in terms of what the ears can actually receive from the external world. To comprehend the auditory mechanism, let us look at this video. This young boy is fascinated to the chirping sound of the little bird. He is crawling and approaching the bird. How does he hear this sound? Look at his pinna. His pinna collects the sound energy that is generated by the bird. This sound travels through the ear canal and strikes his tympanic membrane, that is his eardrum. Here sound energy is transformed into mechanical energy. The oscillation of the eardrum makes the malleus, incus and steps move. Besides transmitting the energy, these bones also amplify the sound. You can see the oscillation of steps in the middle ear. This now presses the oval window and the vibration enters cochlea. You now see the organ of corti. The wave in the cochlea has reached there. The organ of corti has numerous hair cells which act as receptors. The pressure on the waves stimulates these hair cells, which in turn generate receptor potential. This neural firing travels to the brain through the auditory pathway, and the child senses that he is listening to this melodious sound of the bird. We now move to our olfactory mechanism. The receptors of the smell basically respond to chemicals available in our environment. The nasal gland produces odorant binding protein. They are also called OBP. The OBP gets sprayed in the tip of the nose when we breathe. As these glands are little off the root, our sense of smell is relatively dull when we breathe normally. The nasal membrane contains receptor cells for the odors. This membrane is called olfactory epithelium. Olfactory epithelium has millions of receptor cells. Each receptor specializes in identification of a particular smell. Altogether, 10,000 odors can be identified with the help of these receptors. The large number of specific smell receptors carry unique odor signals to the brain. Axons of the olfactory receptors go to the olfactory bulb. Some recoding occurs at this stage. The recoded message then goes to the temporal lobe for conscious awareness. The impulses also go to amygdala and hippocampus, where emotion and memory gets involved to it. Let us look at this video to understand the olfactory mechanism. This young little boy is too fond of roses. He goes and sniffs the rose in his garden. How does he identify the smell of the rose? As you see here, the vigorous intake of air by this boy has made the OBP release in his nose. The receptors at the olfactory epithelium specialize in a particular smell. This unique odor reaches his olfactory bulb. You see the olfactory bulb, olfactory nerve and the mitral cells. You now see the olfactory receptor neurons that are blue, green and red in color here. You can see the OBP release and the conduction of order signal in the olfactory receptor neurons. These order signals are now transmitted from the olfactory neuron to the mitral cells, and finally, the olfactory tract carries the message to the brain. This is how this young boy got the smell of the rose. We now come to our taste sensation. The tongue has small bumps called papillae that contains the taste buds. The taste buds contain receptor cells that are spread at the tip, sides and the back of our tongue. A total number of taste buds in any given adult is approximately 10,000. When you look at the sensitivity of the tongue is not equally sensitive in all given region of it for all types of taste. The tip of the tongue is sensitive to sweet and salty tastes. The back of the tongue is sensitive to bitterness, and the sides of the tongue they are sensitive to sour tastes. The chemical component of the food dissolve in saliva and goes down to the surfaces between the papillae. The chemical interaction triggers the adjacent neurons. The impulse travel to the parietal lobe and the limbic system. Only sweet, sour, salty and bitter are detected by the tongue. The rest of the tastes are actually the combination of them. This young boy is enjoying a chocolate. How does he get the taste of it? Look at his tongue. The tip of the tongue is sensitive to sweet and salty tastes, side to sour and the back to bitterness. You can see small bumps that contain the taste buds. These bumps are called papillae. You can see a taste bud. The chemical components of the chocolate dissolve in the saliva and goes down to the surfaces between the papillae. This chemical interaction triggers the adjacent neurons, and these impulses travel to the parietal lobe and the limbic system of the brain of this boy. This is how he got the taste of the chocolate. We now come to our fifth basic sense, that is the touch sensation. Our skin can distinguish 5 senses: heat, cold, touch, pain and pressure. Sensitivity is not uniformly distributed across the skin. Some point might be very sensitive, whereas other might not be so. Heat and cold sensations have to do with temperature, whereas touch, pressure and pain are variable degree of the touch sensation itself. The temperature of the skin is usually 32 to 33 degree centigrade. The temperature of the blood beneath the skin is about 37 degree. A stimulus of 28 to 30 degree centigrade will definitely be felt as cold, whereas a stimulus of 34 degree centigrade will definitely be felt as warm. The free nerve endings are responsible for carrying temperature related information to our brain. When you look at the touch sensation, some form of arousal at skin surface is essential for cutaneous sensations. If you look at sensation in the palm, the receptive field of cortical neurons are smallest on the fingers and large on the hand and the forearm. The Meissner's corpuscles are sensitive to pressure sense in hairless region of the body. The basket nerve endings are sensitive to pressure sensation in the roots of the hairs, and the Pacinian corpuscles are sensitive to pressure sensation. And as we have been discussing that finally the signal has to reach the brain to get processed, to be understood that yes, you have either touched something or you are experiencing cold, you are experiencing heat, you are able to sense the increase in the temperature and so forth. Till now we have discussed the 5 basic sense modalities. The visual and auditory systems are exteroceptive systems, since they are sensitive to external stimuli. The somatosensory system also has an exteroceptive function. Beside these 5 senses, we have 2 important senses with us, the kinesthesis and the vestibular senses, and both of them they play significant role in our life. Kinesthesis is the feeling of motion of the body parts involved in some form of a movement. So, say if I am now moving my neck, okay, actually only one part of my body is moving, and kinesthesis is actually my own feeling of the motion of this body part of mine. Say when you are supposed to make a desired movement, say you leave a place and then you have to go and occupy a seat, you move towards the chair, you go and sit there. Now, basically you actually also take care of the fact that limited parts of your body makes movement here. So, kinesthesis serves an important function. It actually gives you the perception of the motion of your own body part. The vestibular senses are responsible for making us have the sense of the spatial orientation. For example, how do we know the position of our body in this space? Where am I in this space? So, this type of understanding of the relative position of oneself in the given space is an outcome of the vestibular senses. The sense of balance is another important construct here, wherein we get information about the relative position of the related body parts during movement. Say for example, I just want to remove my spectacles. Now, I know where it actually lies on my body, and then I move my hand, okay, and I do not commit an error. Majority of us whose brains are functioning normally, we will not commit error, and very precisely we go and move it. Now, step by step if you look at it, you have to make a movement, the two palm here is parallelly making a move, okay, and then it moves close to the face, okay, and it is not that say one reaches this point earlier and the other commits a delay. Both of them synchronize together, they coordinate with each other. So, you move here and then accordingly you can move it. Okay. Irrespective of what you are doing, say you are jumping, you are running, you are playing a game, you have a due sense of balance, wherein you know, okay, how your body part is moving, okay, so that there is a perfect coordination between the different parts of the body that actually gives you a sense of balance. You do not fall down. Now, let us look at this video.
These are some of the finest movements that human beings are capable of performing. All this requires extreme degree of coordination.
Remember, the left and the right foot, they do not coordinate with each other, okay, then you will not be able to walk. Okay, forget about very precise movement, even normal walk will not be possible in case these two foot start working independently. Now, when we look at the overall situation in this world, right now you saw the visible spectrum, you saw the audible range. What was very interesting was that we have a range, okay, and on the full scale we have 2 points between which we can receive the information, beyond and below which our sense modalities, they are not capable of receiving the information. Very interestingly, in psychophysical terms, if we look at it, we actually will come across 3 different types of values. Okay. In behavioral sciences, we call them absolute threshold or absolute limit, difference threshold or difference limit, and terminal threshold or terminal limit. Absolute limit is actually the minimum intensity of the stimulus that can be detected 50% of the time. So, if you are shown something and 50% of the times you say that yes, I did see it, only then that point will be considered as the absolute limit for this vision to take place. Say for example, when you have a sudden flash on the television screen, you do not see what was actually shown there. But then if I increase the duration, the exposure duration, okay, and that exposure duration where you claim that yes, 50% of the times you claim that yes, I did see, okay, that would be considered as absolute limit, and this would be true for all sense modalities. Then we come to something called difference threshold or difference limit. This is operational when you have to make a distinction between the absence and the presence of the second stimulus now. So, this is the smallest difference between the two stimuli that can be detected. So, you have say 0.1, and when 0.2 also comes there, and till you say that yes, I now see 0.1 and 2 both, okay, below this, okay, you have not reached the difference limit. The point where you say that yes, now I can see two things, then this point will be called as difference limit. The example you can have from your day to day life, say when you move the knob of your audio system, your radio, your tape recorder, any audio system, you just move the knob, and when you move it, actually with each jerk that you give to that instrument, okay, there is some increase in the physical quality of the sound. So, physically the volume increases, but when you listen to it, you do not sense that yes, the volume has increased till the movement of the knob reaches a particular point where you say that yes, now I can make a distinction that the volume has increased. So, this point will be considered as the difference limit. This is the smallest difference point where you say that the volume had not increased, and from where onwards you say that the volume has increased. So, if you take a straight line, okay, and you say that okay, no, even though the knob is moving, you say that yes, physically the knob is moving, okay, and you come up to this point and you say no, that volume did not increase. So, although there is a change at the physical continuum, okay, psychologically you do not perceive that the change has actually taken place, and this is the point where you say that yes, I can now sense that the volume has increased. Okay. This is the difference limit. And then we come to the third concept here, that is called terminal limit. This is the threshold at which the original sensation changes to another sensation. Let us take the same example. You keep on still increasing the volume of the music system. So, say from this point you came up to this to say that yes, the volume has increased, and if you further keep on increasing it, a time comes when music converts into loud noise. So, actually what has happened, the original sensation that you had has actually changed into noise, it is no more music for you. Okay. So, this point, this threshold, this limit, okay, where the previous sensation gets converted into another sensation, this is called terminal limit. Along with the concept of limit, something that also needs to be understood is what is called as JND, just noticeable difference. Just noticeable difference or JND is the smallest level of difference between two given points of a sensory stimulus that can be detected. Let us look at the application of this concept of just noticeable difference. I will now give you another example from the real life situation where the change of the brand name took place and how gradually it was done. Okay. Before I explain, just focus on the logo of the brand that you see here. You see here IBM, this was the change that was introduced. So, still you have IBM, the way it was written in the previous condition, it was tilted on one side, now it was straight, okay, and then it also said laser printer 4029 by Lexmark. This was step 2, and then come to stage 3. Now, IBM was removed. Now, it simply says IBM laser printer 4029 by Lexmark. Now, basically you see a change in the brand name, and this is what finally came here, Lexmark on the top and laser printer 4029. IBM was completely wiped out. Now, for those who look at the positioning of a brand, and when you think in terms of the change in the brand name, okay, this was a deliberate attempt to position the changed name that does not reach the JND, the just noticeable difference. Now, if you rerun the whole thing, okay, here you this was the established brand, IBM was the established brand at this point. Okay. You are introducing a change, you are introducing a Lexmark printer, okay. But then you retain everything together. The change between stage 1 where you have the IBM and stage 2 where you have IBM and then in small fonts written laser printer 4029 by Lexmark, okay, is not very prominent here. Okay. Therefore, a deliberate attempt has been made that the change that is introduced here in the brand name should be below the just noticeable difference, so that people do not consider that the previous condition and the present condition has undergone big change. Okay. This is with you should not compare the this very condition, the third condition with the first condition. This third condition has to be compared with condition 2, where you find again that a deliberate attempt has been made to take care of the just noticeable difference. And between 3 and this one, okay, you remove few things and you dislocate few things. Okay. So, this is how even in the real life situation we have taken this example. You can still find out several examples. There are examples where even the model who was actually advertising, endorsing a product, okay, over a span of approximately 30-40 years, okay, 6 different models were used to endorse the brand, but then the change in the model, okay, was deliberate attempt was made, so that the change between model 1 and model 2 does not cross the JND, the just noticeable difference, so that you do not sense that actually there was a change. Okay. You see as if the model was the same, okay. And over years for 30-40 years 6 different models came, okay. 6 different models endorsing the same brand, but then if you compare model 1 with model 2, you find that it has not reached, it has not crossed the noticeable difference limit. Okay. 2 and 3 the same thing, 3 and 4 the same thing, 4 and 5 the same thing, 5 and 6 the same thing. But when you compare between 1 and 6, you realize, oh, there was a huge change, and you identify that yes, these 2 models are actually different. But the present model with the immediate past model, you fail to make a distinction between the 2. This is the application of JND. With our discussion on sensation, we will now discuss perception when we meet next. This is now time for us to recapitulate what we have discussed with respect to the perceptual processes.